Okay, sure. So Shayan, are you ready?
Yeah,
So,
sure.
hello, and this is the finale of Prague Summer School, the last lecture of Shayan about high-dimensional expanders and relation to polynomials.
Okay, hello everyone. So I first wanted to, the last lecture was a bit quick. I just wanted to summarize what we talked about in the last lecture. Uh, so remember, we wanted to prove, we were designing this induction sort of to prove that a given polynomial is log concave. So the final format of the proof looks like this. Let's say you have a polynomial P. You want to prove that P is log concave. Okay, so then you want to prove that P is log concave over the whole, Rn, like positive non-negative ortho. So you say that, so given P, and given, let's say, a point A in non-negative reals, I want to show that P is log concave at A. Okay, so you said I'm going to do this inductively. How would I do it? So the first observation is that first of all, by log concave at P at A, I mean that the Hessian of log of P at A is negative semi-definite. So that's what you want to prove. Now, the first observation is that this is equivalent to the directional derivative of P in the direction A to be log concave at A. So the Hessian of log of P at A is negative semi-definite. So this connection simply follows from this equivalence of log concavity and the fact that the Hessian has n-1 non-positive eigenvalue and only one positive eigenvalue. Basically, you can relate Hessian of P and Hessian of directional derivative of P along direction A. Basically, they are the same up to a normalizing constant, and then you can say that therefore one has at most one positive eigenvalue if and only if the other one has at most one positive eigenvalue. Okay, so first you use this step, then you say, okay, how would I show that directional derivative of P along direction A is log concave? You say that I do this by induction. So first I assume that partial Z1 of P, partial Z2 of P, all the way to partial Zn of P are log concave, meaning that the partial derivatives of P are log concave, and these together with intercomposability So these together in the composability implies what we want. Implies that the Hessian of log of directional derivative of P at A is negative semi-definite. Or in other words, dA of P is log concave. Okay, so just to remind you, how did we do this last step? So the idea was, I'm going to do this for a special case. So let's do it for two variables. Let's say I want to show A1 partial Z1 plus A2 partial Z2 is log concave. So I use this idea. So I have two polynomials. So basically the idea is this: I know by induction hypothesis that A1 partial Z1 of P and A2 partial Z2 of P are log concave. Okay, so this is what induction hypothesis implies. So now you want to say the sum of two log concave polynomials is log concave. How would you say that? It's enough to say that they have a same derivative. So they have a common interlacer. That was the point we were saying last time. So what is the common interlacer of the two? So for this one, I'm going to take A2 partial Z2 of this polynomial of A1 partial Z1. And for this one, I'm going to take A1 partial Z1 of this polynomial. Okay, these are the same by definition. Okay, so now these two partial derivatives have a common interlacer. The only tricky thing is to make sure that this is not equal to 0. Okay, this common interlacer is not equal to 0, and this fact, this not equal to 0, basically follows from indecomposability. So that's why the proof was a little bit more tricky, because you have to first use indecomposability to say that there are many pairs ij such that partial zi partial zj of p is not 0. These pairs basically form a connected graph, so you can reorder them and get something like this. But essentially, this follows from indecomposability. So now these two polynomials have a common interlacer. This implies that the sum of the two polynomials, which is a1 partial z1 of p plus a2 partial z2 of p, is log concave. And now you can inductively do the same thing until you get a directional derivative of p along direction. Okay, so this was sort of a gist of the inductive proof that we talked about last time. Now, if you think about this proof, what do we so now repeatedly apply the same argument to partial derivatives of p and go down and down and down. What do we actually use in this inductive proof to say that p is log concave? What we actually use is two facts. We use the base case. The base case is when you get to a degree 2 polynomial, and we use indecomposability. So what you need to say to say that the polynomial, what you need to show to say that the polynomial is log concave is that all partial derivatives of the polynomial are indecomposable, and that when you take enough derivatives until you get to a degree 2 polynomial, that degree 2 polynomial is log concave. Okay, so this is basically the main theorem that you get at the end of the day, which is that you have a polynomial p, and again, this is for dehomogeneous polynomials. You have a polynomial p, it's dehomogeneous. If it satisfies these two conditions, the first one is that if you differentiate enough, so here by kappa I mean a vector, kappa is a non-negative integer vector, and by partial of kappa I mean partial z1 to the kappa 1, partial z2 to the kappa 2, etc. So you differentiate enough until you get to a degree 2 polynomial, all possible ways. You want that thing to be log concave. That's the first property. The second property is that any number of times you take partial derivatives before getting to a degree 1, if the degree remains at least 2, you get to you still get an indecomposable polynomial. Okay, so if you have these two properties, then p is log concave. Okay, and the thing is, these two properties are basically necessary as well, because in the last lecture we saw that indecomposability is a necessary condition for log concavity, and the base case, of course, the base case you also kind of need it. You have to think about it, but you can basically let some variables to be infinity and you get to the base case essentially. So so as we said in the last time, this implies that basis generating polynomial of any matroid is log concave. I want to say one more thing before we change the topic. So there is a more general, so I talked about log concave polynomials. There's a more general class of polynomials that are called, that we call them completely log concave polynomials. So what is this class? You say a polynomial p with non-negative coefficients is log concave if for any, say a1 up to ak being non-negative and k is an integer, dA1, dA2 up to dAk of p is log concave. Okay, so So what does this definition say? It says that not only I want P to be log concave, I want all directional derivatives of P along non-negative ortho to be log concave. And this is very important because this is again a generalization of a similar fact about real stable polynomials. For real stable polynomials, you also have this property. If you take directional derivatives around positive ortho, you get they're closed basically on the directional derivatives along positive ortho, and complete log concave polynomial have this property as well. Now, okay, so now the question is, how would you show that the polynomial is completely log concave? It turns out that the same proof shows that the polynomial is completely log concave. Because remember that the sketch I was discussing right here, actually we showed that the directional derivative of P along any A is log concave as well. So basically you can follow the same proof. So I can just change this theorem to say that instead of saying P is log concave, I can say P is completely log concave. So if you know that all partial derivatives of P are indecomposable, and when you take enough partial derivatives until you get to a quadratic, it is log concave, then you know that the polynomial is completely log concave. Okay, so that's the main theorem that was shown. I should say there is a different notion defined by Peter Brandon and Juni Hall. It's called Lorentzian polynomial, and they're closely related to this. They're basically similar type of ideas with different terminology. Yeah, okay, so let me, okay, I want to just conclude this part. So let me just say two things about these completely log concave polynomials. First, there's a limitation similar to real stable polynomials. The support of any multi-affine homogeneous log concave polynomial comes from basis of a matroid. So support of any multi-affine homogeneous log concave polynomial is basis of a matroid. So you still get the same limitation that you would have for real stable polynomials, but now the advantage is that any matroid can be realized as the support of a log concave polynomial. So you capture all matroids, but you cannot go beyond matroids. That's the message you want to keep in mind. The second property is that I said real stable polynomials satisfy so-called the negative correlation property. These polynomials do not, but they satisfy so-called approximate negative correlation. I'm not going to get into it. If you want to look at it, if you want to know about it, look at assignment 4. There's a problem about negative or approximate negative correlation property of this polynomials. So basically, this shows that uniform distributions over matroids are not, over basis of a matroid is not negatively correlated, but it's approximately negatively correlated. Okay. So that's all I wanted to say about log concave polynomials. Are there any questions?
I have a question about this relationship to matroids. So is it true that the matroids that can be realized in this way by real stable polynomials for some natural family of matroids, or is it?
Oh, matroids which can be represented by real stable polynomials.
Yeah.
Yeah, any matroid can be represented by log concave, but for real stable, you definitely need. Okay, so first of all, it depends what you mean by being represented. So do you mean by having a
in this way that there exists
that the support is
support is on the basis
with some coefficients. I don't think that is well understood, as far as I know. We just know there are some matroids which cannot be cannot be represented by real stable polynomials for any set of coefficients. Like Fano matroid is one, but I don't know any characterization of which matroids can be realized that way. If you want the uniform constant coefficient, like coefficient of 1, we know more. You basically need the matroid to be negatively correlated. So that's a much limited classes of matroid. So for example, linear matroids, you can realize them as real stable polynomials because of this linear matroids over the infinite, over the real domain. You can realize them by real stable polynomials using this so-called mother of all stable polynomial theorem that we talked about, but not with constant 1. If you want to get them with constant 1, you most likely don't get a real stable polynomial because they're not negatively correlated.
Okay, yeah, thanks.
Any other question?
So we have that the uniform distribution over the basis of a matroid. That polynomial is known to be log concave, right? But if the distribution is not uniform, do we?
That is, yeah. So we don't, I mean, for some other distributions, there are still some results, but in general, I mean, no, there is no reason that if a distribution is not, if you give me an arbitrary distribution, I don't know, you can, it may or may not be log concave. I mean, you can imagine, in general, it shouldn't be, right? Because you can make some coefficients very, very small and the rest of them equal to 1. So practically, even though the support is correct, the very close to 0 coefficients do not really matter. So practically the support of your polynomial is just a subset of basis of a matroid, which is not really a basis of another matroid. So it doesn't work that way. Yeah, it's not true that for any set of coefficients this works. One other thing I wanted to say was that we have a test we have a polynomial time test to see if a given polynomial is log concave or not. All you need to do is to check in the decomposability and log concavity when you look at partial derivations up to a degree 2. Okay, I'm not saying that's a very efficient test. You have to test exponentially many possibilities for all the ways you get to degree 2. When you get to degree 2, you just need to look at the Hessian of the polynomial and see if it has exactly one, at most one positive eigenvalue. But in decomposability is also not so hard to check. You just need to look at the Hessian again and see maybe not going all the way to degree 2, at any degree in between, and see if the Hessian again has at most one positive eigenvalue. So you can test if I give you a polynomial, you can test. You can run an algorithm to test if polynomial is log concave or not, but you don't have such a thing for real stability. If you give me a real stable polynomial, it's not easy to test whether that polynomial is real stable. Okay, and I think even, I'm not quite sure, but I think I heard from some people that it can be NP complete. It's NP complete in general. Okay, so good. So now let's go to the topic of this. Yeah, sure.
In the real stable setting, if we have a polynomial which is real stable, and if we have a marginals that comes from the, let's say, spanning tree protocol, then we can find the external field that converts our original distribution to a new distribution, which is also real stable and satisfies the marginals, right?
Yeah.
Do we have the same property for the log concave polynomials as well?
Yeah. So that machinery I told you about, sort of applying the external field, that works for any polynomial, for any class of polynomials with non-negative coefficient. The main limitation is the computability. So in order to apply that machinery, you need to be able to compute the external field. And in order to be able to compute the external field, you need to be able to evaluate the polynomial and its derivatives, because you need to run some ellipsoid algorithm or interior point method. So you need to be able to evaluate the polynomial and its derivatives. Now, what I'm going to talk about today is that you can evaluate a log concave polynomial, any log concave polynomial, any say homogeneous log concave polynomial, as long as you can evaluate its coefficients. So if you have an oracle that given any monomial, it says what is the coefficient of that monomial in this given polynomial, then you can evaluate the log concave polynomial. And once you can evaluate the log concave polynomial, now you can apply the same machinery, solve a convex program, and find this external field.
Okay, I see.
Any other questions?
So here is also a question. So in lecture 2, we show that real stability implies log concavity. So my question is, could log concavity together with other some conditions imply real stability?
With other conditions. So it depends what you mean with other conditions. I mean, you need to be able to exclude some matroids, right? So what does other condition?
Okay.
I mean, you can, if you look at the structure of the roots, then sure, you can get real stability, but the log concavity become pointless. So I don't know if you can just look at, say, the geometry of the function, as in like convexity, concavity type of thing, to argue that it is real stable.
Oh, okay. Yeah, just curious about the other way around. Okay.
The other way around should not work as easily, right? Because this is a strictly bigger class of polynomials, right? You can realize many objects that you couldn't do with real step polynomials. So if you want to go from this class to this smaller class of real stability, you should be able to exclude that object. And I don't see a simple way to do it.
Okay, I see.
Other questions?
Oh, maybe another question is about the definition of the completely log concave. So here we use the notation of capital D. So can I see this is a little bit stronger than saying all the types of partial derivatives of P is log concave?
This is saying all directional derivatives of P are log concave. So you can So you can differentiate, like you can look at partial Z1 plus partial Z2. That could be D of A1, and D of A2 could be partial Z1 plus partial Z3 plus 10 partial Z9. That could be A2 and so on.
Yeah, so this is stronger, right? Yeah,
this is a stronger property, but it is equivalent. So the fact that the polynomial is that all partial derivatives are log concave is equivalent to the fact that all directional derivatives are log concave. It's not obvious, but it follows from this proof.
Oh, okay, I see it.
Okay, so good. Any other question? Okay, so let's get to the topic of this lecture. So as I said, to these questions, the main goal is to be able to evaluate log concave polynomials. Having access to the coefficients. So let's say you have an oracle that if you give a monomial, it will spit out the coefficient of that monomial. Now you want to use this oracle, maybe call it multiple times to evaluate your log concave polynomial. Okay, and this is just to tell you, as a consequence, this would show that this would show that you can count the number of bases of a matrix, of any given matrix, as long as you can test whether a given set is a base or not. I should say also that there is equivalence of so-called counting and sampling. So if you can sample, say, a base, that's equivalent to approximately counting the number of bases. And similarly, if we can sample a monomial of a polynomial, of a log concave, say, polynomial or log concave distribution, it's equivalent to evaluate that log concave polynomial approximately. So sorry, and I should say this evaluation will be approximate, right? So we're going to do approximation, like 1 plus or minus epsilon approximation, multiplicative. Okay, and the running time that, I mean, I'm not going to prove this running time. I'll see how much we go, but the best running time that now there is basically, okay, so we're going to do a Markov chain. We're going to use a Markov chain, and there's a Markov chain that after say order of r log r, essentially, over let me ignore the dependency on epsilon. It gives a random monomial. Okay, sampled proportional to its coefficient. So that's where we are heading. Okay, so let me tell you the main object that we're going to work with to get close to this goal. The main object is called simplicial complex and high dimensional expanders. So what I'm going to do now is that there's going to be a series of definitions and some observations, and then we'll see connection to polynomials. Okay, so the main object is simplicial complex. So simplicial complex is defined on a set of elements. Say we have a set of elements n, called 1 to n. And a simplicial complex, let's call it X, is a subset of 2 to the n, which is downward closed. So if you have a subset, you also have all subsets of that subset. Let me say, okay, I need a few notation. So I'm going to say if sigma is a subset in X, I call sigma a face of X. I define dimension of sigma to be the size of sigma, the number of elements in sigma minus 1. And I define dimension of X to be maximum over all sigma, all faces in X of dimension of sigma. Okay, so we define a dimension for the complex as well. I write X of K to denote all faces such that dimension of sigma is K. I'm going to show an example in a second. And one more thing, I say X is pure simplicial complex. X is pure if sorry, let's say dimension of X is D. So I say X is pure if for any sigma in X such that dimension of sigma is less than D, there exists some tau in X with dimension of tau equal to D such that sigma is a subset of tau. Okay. In other words, if you have any phase of codimension more than 0, which is any phase which is not a top phase, not a maximal phase, there is a maximal phase which is a superset of the given phase. So okay, so now examples. So example 1 is called the clique complex. So let me draw this graph. So let A, B. So here we have a graph and a clique complex. In a clique complex, every face is a clique. Okay, so this graph, the largest clique is a triangle. So the dimension of the complex, the clique complex that you get here is 2, because a triangle has 3 vertices, so it has dimension 2. Okay, so in the clique complex, every face is a clique. Here, maximal faces are triangles. And this is not a pure simplicial complex, because there are many faces. Oh, sorry, this one in particular, this one in particular is pure, but in general, maybe if I add this extra edge, if I add H, let's say, then it's not pure anymore, because if you look at the edge EH, it's not in any maximal face. So after adding this extra edge, it's not pure. The previous one was pure. Now, example 2. This one will be more relevant to us. So example 2 is the independence complex of a matroid. Independence complex. So given a matroid M equal with n elements and independent sets I, here X of M has a face for every independence. Okay, so every independent set would be a face of my complex, and the reason that this is a simplicial complex is that it's a downward closed property of faces. If you have of independent sets, if you have an independent set of a matroid, remember every subset of that independent set is also independent. So that's why this is a simplicial complex. And so you have the same property for clique as well, right? If you have a clique, if you choose a subset of the clique, you also get another clique. And that's why the clique complex is a complex. Now, the independence complex is pure because this follows by exchange property of the matroid. Basically, so remember, if you have a matroid complex or an independence complex, the maximal faces are bases. Now, if you have a face which is not maximal, meaning that independent set which is not a base, then we know that there is a base that contains this guy. So you can, so there's a base containing this guy, and that's the reason that it's a pure complex. Good. So far, so good. Any questions so far? Okay, so so let me just, okay. So I'm gonna do, now I wanna define, like where I'm heading to is I'm gonna define weight distribution or probability distribution on complexes, and then I'm gonna define a random walk on a simplicial complex. So the one thing I hope you have taken a look at is the background notes on random walks. That would be very crucial for us. So we're going to define, so let me just remind you of this definition. So if you have a graph G equal V comma E, and let's say P is the random walk, a simple random walk matrix on G, simple random walk operator. Then we say G is a two-sided lambda spectral expander if basically lambda star of P is less than or equal to lambda. And lambda star is basically equal to max of lambda 2 and absolute value of lambda n. Okay, this is the second largest eigenvalue in absolute value. And we say G is a one-sided lambda spectral expander if lambda 2 of P is less than or equal to lambda. Okay, so there is a lot of literature in and applications on spectral expanders in TCS. You know, even in complexity theory, I assume Subhash has used them a lot in his lectures as well. But basically, the thing in Markov chain or random walk mix, random walk basically starting from any vertex, mix rapidly, go to the whole graph very rapidly. If this lambda is a constant, so we're interested in the cases that this lambda is bounded away from 1. So think about something like 1/2 or 2/3, something like that. So they have a very small diameter, about log n, and they have so-called expansion properties. Every set of vertices have a lot of about constant fraction of edges going outside and so on. So the objective that we have here is to define a high dimensional spectral expander. Okay, so let me so before that, let me first define this oops. Let me first, sorry. I don't know what I did. Sorry. First, let me define a notion of assigning weights to faces of a complex. So let me work with the same clique complex I was defining above. I tried to copy it, I couldn't do for some reason. So let me just write it down again. Okay, so let's say we assign a weight to top faces of this complex. Here we have 3 triangles. So assign uniform weighting or uniform distribution to triangles. Okay, so we have three triangle. The weight of each of them, or the probability of each of them, will be 1/3. Okay, so I'm going to write pi2 to denote this. So pi2 of, say, this triangle ABC is equal to 1/3. And similarly for all triangles. Now, here's a interesting thing. Say you start with a distribution on top faces. This induces a distribution on faces of a dimension 1 less. This finds a distribution on edges. So how would it do? You start with a triangle, you knock down a vertex uniformly at random, that would give you an edge. So pi1 of an edge, A comma B, is equal to the probability that, say, you choose a triangle sigma according to pi2, the probability that A comma B is a subset of sigma times 1/3, right? Why do I get 1/3? 1/3 is the probability that I knock down a vertex. Okay, so if you want to get from a triangle to AB, you need to knock down one vertex such that the remaining vertices are AB. So the probability of, so in this particular case, probability of AB is exactly 1/3 times there's only one triangle which gives me AB. That's the triangle ABC. So it's 1/3 times pi2 of A comma B comma C, which is equal to 1/9. So another example is the pi1 of say BC. So this is equal to 1/3 times pi2 of A comma B comma C plus 1/3 times pi2 of B comma C comma D, which is equal to 2/9. Okay, so you can keep going, and you actually get a distribution over edges. This is 1/9, 1/9, 2/9, 1/9, 1/9, 1/9, 1/9. You see that they add up to 1, hopefully. So you also, so you can keep, so sorry. The thing is, this operation I just did, you can do the reverse. You can start from, okay, now let's say you have a distribution over edges, as I explained. You can get back a distribution over triangles. How would you do that? First, you choose an edge based on pi1, and then you choose a triangle condition on that, conditioned on that edge. Okay, so for example, I'm saying basically this. Let's look at this triangle ABC. Pi2 of ABC, I'm saying, is equal to pi1 of AB times probability of ABC condition on AB plus pi1 of BC times the probability of ABC condition on BC plus pi1 of the other guy, AC, times the probability of ABC condition on AB. Okay, now let's rewrite this down. So this is the first line. This is 1/9. What about probability of ABC condition on AB? What do I mean by that? I mean that you have this edge AB. Now you want to choose a triangle based on AB, right? So you say that, look at all triangles that contain AB. I choose one of them with probability proportional to the weight of that triangle. Okay, so in this particular case, there's only one triangle which has AB, so this guy will be 1. Then this guy is 1, this is 2/9 now. The edge BC. Now, if you choose BC, there are 2 triangles which contain BC. You choose one of them with probability proportional to its weight, pi2. because the weight on triangle is uniform, you choose one of them uniformly. So this guy would be 1/2. And similarly, this is 1/9 and this is 1. So you get back 1/3. Okay, so I should say again that by this probability of, let's say if you have a triangle sigma, probability of sigma condition on AB, by that, I mean the following. I mean, basically pi2 of sigma over a summation of all tau, which is a superset of sigma of AB, pi2 of tau. That's what I mean by choosing a triangle proportion, like triangle condition on being on an edge. This operation, so if you look at my notes on random walks in graphs, this is very similar to what you do on a graph, except that instead of doing this for triangles and edges, you do it for edges and vertices. If you have an edge, you go to a random vertex by deleting one of the endpoints uniformly at random. And when you have a vertex, you go to a random edge by choosing one of the edges that contain this vertex proportional to its weight. Here we're doing the same thing, but just on one higher dimension. Given a triangle, we go to an edge by dropping a vertex uniformly at random. Given an edge, we get a triangle by looking at all triangles that contain this edge and choosing one of them proportional to its weight. And the observation is that these two operations exactly give me the same thing. Okay, I can start from triangles, go back to edges, come back to triangles, I would get the same distribution, and vice versa. I can start from edges, go to triangles, come back to edges, and get the same distribution. So in fact, you can follow the same procedure from pi1 to pi0. Pi0 will be distribution on edges, on vertices. So you have an edge, you want to choose a vertex, you drop one of the endpoints uniformly at random. So what would be probability, let me write it with blue, what would be probability of say vertex C, right? So you should choose either the edge AB or BC or DC and choose the other endpoint to keep C, right? So the probability would be 1/2 of 1/9 plus 1/2 of 2/9 plus 1/2 of 1/9, which would be, the probability of C would be 2/9. The probability of A would be 1/9. The probability of B would be 2/9. The probability of D would be 2/9 as well. 1/9, 1/9. So as you see, I started with a uniform distribution over triangles. Now I have a distribution over edges and a distribution over vertices. And I can follow this back up, start from vertices, get edges, and get triangles. Okay. So this is how I define a distribution. More generally, you can do such an operation for any simplicial complex and for any dimension k. You can start from faces of dimension much more than 2, like so triangles, you can go to higher dimensions and start. So all the time, what we do is first we assign weights or distribution on very top faces, and then we go all the way down. So I'm going to adopt this notation. When I write sigma sample from xk, I mean basically sigma sample from pi k. Okay, I just write xk to make sure that this is this complex. Okay, any question? Okay, so we need the next object, links. Hopefully then we'll be able to say a little bit. So a little more math. So what is a link? So let's say you have this complex X. You look at an element I. X of I is defined as follows. It's a set of sigma such that sigma union I is a face in X and I is not in sigma. So what is this operation? I'm basically contracting. So this is, think about, this is basically, if X was a matrix, this was exactly the contraction. You look at every face or every independent set which has I, and you drop, you exclude all other independent sets or all other faces, and you remove I from those that have I. That's exactly contraction. Okay, if this was a graph like a clique complex I was talking about, X of I is exactly the neighborhood of a vertex. You look at all edges or all triangles which contain this vertex, and you drop that vertex. Okay. Now, more generally, you can define X of a tau. If you have a face, you can define X of a tau, and this would be all sigma such that sigma union tau is a face and sigma intersection tau is empty. So it's basically, again, if you have a matroid complex, this would correspond to contracting tau in your matrix. Tau here can be more than one vertex. It could be multiple vertices or multiple elements. Okay, so so actually, let me draw the same graph again. So it was A, B, C, D, E, F. So remember, we had a uniform distribution over faces, and that gave me a distribution over edges, which was 2, 9, 2, 1, 9, 1, 9, 2, 9. Okay, now let's say I look at X of C. What is the link of X of C? The link of X of C is a simplicial complex itself. It has the following faces. It has the empty set. Empty set is in every simplicial complex. It has the empty set. It has vertices A, B, and C. And it has edges A, comma B, and B, comma D.
Okay. Sorry, so it's the vertices are ABD, right? No,
ABD, sorry. ABD, thanks. Yeah, ABD. Yeah. ABD. It has vertices ABD and edges AB and BD. Okay. Now, again, remember we had this distribution over the original complex. This defines the distribution over this new complex. Basically, the way you do it is there are multiple ways to think about it, but basically it's a conditional distribution. That's the point. So one way to think about it is that I look at the triangles in the original complex. I had the uniform distribution. So I look at the conditional distribution here. So here now, the probability of this guy would be 1/2. The probability this guy would be 1/2 because I had a uniform distribution. So I have now still a uniform distribution on top faces. So it would be 1/2, 1/2 here, there. Then the probability of B now would be 1/2. D would be 1/4. A would be 1/4. Okay, so one thing to note is that I'm not saying basically pi1. Let's write this as pi1 of X sub C of A. Okay, meaning that probability of A in this new complex XC. I'm not saying this is not basically equal to pi. That should be pi 0. It's not equal to pi1 of X of A comma C, because I'm renormalizing. Pi1 of A comma C here was 1/9, whereas probability of A here is 1/4. It's a conditional distribution. I look at basically all of the if you look at AC, BC, and DC, these are the edges that would I would drop C and they would stay in my new complex. So AC, BC, and DC, their probability was 1/9, 2/9, and 1/9. So the conditional probability of A would be 1/9 over the sum, which is 1/9 plus 2/9 plus 1/9, which would be 1/4. Right? So this probability is basically equal to 1/9 over 1/9 plus 2/9 plus 1/9 is equal to 1/4. So you can think about it in two ways. One way is to think about, you look at the conditional distribution of the top faces in the new complex, which would be, say, uniform. So you would have uniform over AB and BD, and then you do the same process by knocking down to get to the vertices and so on. So that's one way to get the probability of A, B, and D. Another way is to just say, okay, look at probability of AC, BC, and DC in the original complex. The probability of AC would be the conditional probability. Condition and this, what is the probability of AC? That's 1/4. Okay, so I'm going to use this notation now. When I write, for example, sigma sampled from x of tau of k, I mean sigma sampled from pi x tau of k. Okay, any question? Okay, so now we get to the interesting part. Again, as I said, this lecture we're going to go over time. I think we'll probably go 20 minutes over time. It's the last lecture, hopefully you allow me. So now let me try to gain from this or build some stuff. So the main sort of insight or main point of studying these complexes is a method called Garland's method. This is a method developed in 70s, and basically it's called localization. So the high level intuition is that you can calculate many quantities of your interest by evaluating those quantities on the links of a certain dimension, sort of localizing it. Instead of studying something at a very high dimension, you can locally study the same quantity on the links and sort of average it out over your links with respect to the distributions that I define. Okay, so I'm gonna do an example formally here, but in the interest of time, I'm not gonna do every calculation. You can do it later on for yourself, but I'm gonna do a simple case of localization. So let's say you have you have two functions f and g, where they assign a weight to every face of dimension k. Okay, we define the dot product between f and g, which is as follows. It's basically equal to summation of sigma in xk pi k of sigma f of sigma g of sigma. Another way to think about it, it's exactly expectation of sigma sampled from xk of f sigma g sigma. Okay, you choose a random phase of that dimension based on this probability distribution pi k, and then you calculate the expected product. Now this also defines a norm. The norm of a vector f is basically the dot product of f with itself. And I may drop the xk here when the complex is clear on the underlying complex is clear. Okay, so now here is a simple lemma. Say you have a simplicial complex x. Let's say you have these integers, L less than K, K is less than or equal to D, L is more than or equal to 0. So, and you have two functions, f and g, that map xk to real numbers. Here's the point. I'm interested in the dot product of f and g. I'm saying it's equal to the following. You first sample sigma from XL, and then you look at f of sigma, g of sigma. This is with respect to x of sigma of k minus L. So what do I mean by f of sigma? F of sigma of tau, sorry. So f sigma here is called the so-called the localization of f. So this is called localization. So it's equal to, so f of sigma of tau is basically equal to f of sigma union tau for tau in x of sigma. Okay, so what am I doing? What is a localization? You look at, you have this function f. You look at faces in, you have this function f defined on faces of dimension k. Now I fix some sigma of some lower dimension L, and f of sigma for any tau of dimension, say k minus L minus 1 in the link of sigma, f sigma of tau is just f of sigma union tau. It's basically, I'm looking at all faces which have sigma, I contract sigma, I just look at, define the tau to be that. Okay, so this is called localization. And so what is the point of this lemma? I'm saying to calculate the dot product of f and g, it's enough to calculate the expected dot product of f sigma and g sigma for a sigma chosen randomly based on like on a face, for a sigma to be a random face on a lower dimensional on a lower dimension. Okay, so if sigma in particular, if sigma was the empty set, this would be nothing. This would be, if you let sigma to be empty set, then f of sigma is the same as f. But when sigma is bigger, this would become interesting. So another way to think about this lemma is that to calculate the norm of a function, it's enough to calculate the expected norm of this function localized to different faces. Okay, and this would be, I mean, you can imagine now that this would be important because eventually we're going to talk about eigenvalues of some huge matrices defined over this complex. So when you want to talk about eigenvalue, you want to say, for example, what is the norm of PF? You want to compare the norm of PF with respect to norm of F. So this says that in order to calculate that, it's enough to calculate the average of norm of F on the localized links. So how to prove this? I'm going to prove this one, but not, and this will be the only one I'm going to prove in the interest of time. So I'm interested in the dot product of f and g, xk. So this is equal to expectation of tau, sample from xk, f of tau, g of tau, by definition. Now I'm saying this is equal to the following. So first sample sigma from xl, then sample tau in xk, condition on sigma, f of tau, g of tau. So I'm saying basically do the following. First you sample sigma, then you sample tau condition on sigma. It's the same thing. It's basically law of the expectation, right? Instead of sampling tau immediately, first you sample sigma, then among all tau that contains sigma, sample tau proportionally. Now, another way to think about the same thing again is that first I sample sigma from XL, then I sample. So we already have a notation for sampling tau from the tau condition on sigma. It means that you sample tau from the link of sigma. And then you look at f of tau union sigma, f of tau union sigma. Maybe actually, let me call this other one tau prime. So the tau I have in the second line, this tau, is basically tau prime union sigma. So I'm saying instead of choosing a face of dimension k, condition on a face of lower dimension sigma, you can sample a face of dimension essentially k minus L from the link of sigma. Okay, and now once you have this guy, this is exactly the dot product of F sigma and G, sorry, this should have been G, F sigma and G sigma in X of sigma, basically. X of sigma of K minus L. Okay. Make sense? Any questions? So it's basically this law of averaging, right? I'm saying it's like this simple fact. I'm saying going below or going above is the same. So first you sigma, then you sample tau condition of sigma, which basically means that you sample tau from the link of sigma. That's it. That's all I'm saying. Okay. So now that we know this, can define spectral link expansion. So let's say you have a complex X. Then let's say it's defined on N. You define one skeleton of X. What is one skeleton of X? This is a graph, let's say G, with vertex set N. And the edge set, it is a weighted graph where, let's say it's at some edges E, where for I and J, the weight of the edge ij is pi 1 of I comma j. Okay, so we have these weights on the edge, on the on simplices of dimension 1. So you define so-called one skeleton of a complex. You have a vertex for every element, for every face of dimension 0, and you have an edge for every face of dimension 1. And the weight of that edge is exactly the probability of that face of dimension 1. This is called one skeleton. Now, we say that X is a two-sided lambda spectral expander if for all tau of dimension of tau less than or equal to d minus 2, it means that tau of codimension 2 at least. P of tau, or let's try to find it this way. One skeleton of X of tau is a lambda, is a two-sided lambda spectral expander. Okay, so in other words, I define the graph. You can look at, in other words, you can define P of tau to be the simple random walk operator on one skeleton of X of tau. Then I want basically lambda star of P of tau to be less than or equal to lambda. And similarly, we say X is a one-sided lambda spectral expander if basically lambda 2 of P of tau is less than or equal to lambda. Any question? So I want every link to be an expand. So this is very interesting. Like if you think about a graph, this is like saying, for example, I want the graph to be an expander, the neighborhood of every vertex to be an expander, the neighborhood of every vertex to be an expander, and so on, something like that. So one example of such a thing is a complete complex. What is that? Let's say you have n, and you have all subsets of n of size, let's say d, or say d plus 1 in X. And these are the top faces, the complete complex. And you have a uniform weight. Okay, then in fact, every dimension, you would have all faces and you would get a uniform distribution. Now, if you look at the one skeleton of this complex for any link, the one skeleton of X of tau, of X of, what do you call it, X of tau is a complete graph. With uniform weights on edges. And a complete graph has second eigenvalue basically equal to -1 over n. So this says that, or I guess -1 over, I should have said, X of tau of 0, the number of elements in the complex. So this basically says that X, our complete complex, is 1 over n two-sided spectral expand. Okay. Another example. Let's say you have a de-homogeneous polynomial P actually let's say D plus 1 homogeneous. Then you can construct, so let's write it this way. It's called P is equal to summation of, say, some sets of size D. Let's call it CP of S. Coefficient of S in P is CP times Z to the S. You can define a simplicial complex here. Let's define it X of P. You have a face of dimension D for any, let's say you have a face S of dimension D for any S such that CP of S is non-zero, and the weight, or let's say pi D of S is exactly CP of. So you give me a polynomial, I build a simplicial complex, top faces are this, and then I take downward closure. You give me a polynomial, I get a simplicial complex. Top faces are exactly the monomials, and the weights are exactly the coefficient of the monomial. But I want the polynomial to have non-negative coefficient in order to have a distribution on top faces. Okay. Now here is a simple fact. I mean, simple to state fact at least, but it was non-trivial that. I mean, sorry, I should say you can do the other way around as well, right? Given a complex x, I can construct a polynomial g of x, the generating polynomial of the complex, by looking at top faces of that complex and construct a monomial for every top face with coefficient equal to the weight. So exactly the same process that I just did, you can do the opposite direction. Now here's a theorem that a d-dimensional complex X is one-sided zero spectral expander if and only if g of x is basically completely log concave. That seems shocking at the moment, probably, but let me, I mean, okay, I don't have time to give you the full proof of it. It's in the notes, you can read it. But let me just say the main idea. Main idea is that let's say you look at X itself. Not, I mean, the same is true for the links, but let's look at X itself. Let's say A is adjacency matrix of one skeleton of X. It's the adjacency matrix of the graph I explained. Then you can show that A is equal to D plus 1 choose 2 Hessian of G of X at 1. So the adjacency matrix of the one skeleton is exactly the same after a normalizing factor. It's the same as the Hessian of the polynomial at all ones. Now, why is that important? Because we said that if a polynomial is log concave, then the Hessian of the polynomial has one positive eigenvalue and the rest are negative. So this says that the adjacency matrix of the one skeleton has one positive eigenvalue and the rest are zero. Now, you can see, you can do a little bit of calculation. The point is, when you go from adjacency matrix to a random walk matrix, all you do is that basically you multiply the adjacency matrix on the left by inverse of the degree of vertices. What that would do is it doesn't change the number of, it doesn't change the signature of the matrix. The matrix still would have one positive eigenvalue and the rest are negative. Therefore, the random walk matrix has second eigenvalue less than or equal to 0. And that would say that, at least for the complex itself, the second eigenvalue of the random walk matrix is less than or equal to 0. Now, what about partial derivatives? When you take, when you take a partial derivative, it's the same as contraction, or which is basically the link of a complex. So partial derivatives are log concave. That says that links of the complex are also expanders as well. Okay, so now you see that basically this whole theory we developed for log concave polynomials naturally extend to these high dimensional expanders. You know that every log concave polynomial gives you a zero high dimensional expander. I should say that, I mean, high dimensional expanders now have a lot of applications in like property testing and coding theory, but those applications are typically for so-called sparse high dimensional expanders. Expanders you get out of matroids are not, or out of log concave polynomials are not sparse. You would have a lot of faces at a lot of maximal faces, exponential in the number of elements n. But ideally, for applications in coding theory, etc., you want to have only linear number of faces in n. Okay, so we're going out of the time I wanted to say. So there's this last part I wanted to say. It's about high dimensional walks. So let me just say this and then, okay, give me like 5 more minutes. Now you have a simplicial complex. You can define a random walk on top faces. How would you do that? Or on anything, or on, like, for any chair, you can also do it. There are 2 random walks you can define. So there's an up-down walk. This is called down-up walk. And there is the up-down walk. So what did a down walk up do? You start from a face of dimension k. You go down. How you go down? You drop one of the elements in that face uniformly at random. You go to a face of dimension k minus 1. And then how you go up? Among all faces that contain this guy, you choose one of them proportional to its weight. Then you go up. What is the up-down walk? It's the reverse. You first go up. You start from a face of dimension k. You go to a face of dimension k plus 1 by choosing one proportional to its weight. You first go up, and then you go down by dropping one of the elements. So pictorially, the way you want to think about it is this. You have this graph. You have the empty set here. You have x of 0 here. You have x of 1 here, x of 2 here, and so on. The down up walk starts, let's say P of P3 of down up starts here, goes down by dropping one of the elements uniformly at random. You go here, and then you go up by looking at every face that contains this guy and choosing one of them proportional to its weight. Then you go up. The up down walk, you start from here. You first go up, you choose one of the faces that contain this guy, and then you go down. So the simple random walk you do on graphs is basically so simple random walk on graphs is the same as P0 up down. You start from a vertex. You choose an edge proportional to its weight, an edge which is a neighbor of this vertex proportional to its weight. You go to that edge, then you drop one of the endpoints of that edge. So this walk is so-called half lazy. Because when you go up, I said you drop one of the endpoints of the edge, right? So with 1/2 probability, you drop the same endpoint, you go back to the same vertex that you started with. So probability half, you go back to the same vertex. So this walk is half lazy. And in general, pk up down is 1 over k lazy. Is 1 over, sorry, k plus 2 lazy. Okay. So this walk is basically a simple generalization of the walks we usually do on graphs. But now you sort of oscillate between these faces of dimension k minus 1 and k, or k and k plus 1. So for the case of matroids, for example, you can run this walk on bases. Your bases would be, say, top faces, and your near bases would be the one below. You start from a base, you drop one of the elements of a base, you go to an independent set of size r minus 1. Then among all bases that contain that independent set, you choose one of them uniformly at random. You go back up. Again, you drop one of the elements of a base, you go to an independent set of size r minus 1. Then among all bases that contain the independent set, you choose one of them uniformly at random, and so on. Okay, so now the main result is that the theorem is that if X is a one-sided zero spectral expander, then lambda 2 of P, make sure I write it correctly, lambda 2 of pk up down is less than or equal to 1 minus 1 over k plus 1. Okay, so this lambda 2 is bounded away from 0, and that says that for the case of matroid, this k is about r. You run it, it's a rank of the matroid. So this says that the second eigenvalue of this giant walk you're running on bases and near bases has second eigenvalue bounded away from 1. So immediately from this, you would get that if you run this Markov chain for r times log of the number of bases, you would mix. But there are better bounds that you don't actually need to run for r times log of the number of bases. Something like r times log r is also enough. Okay, so let me tell you the main. So how to show this? I just wanted to tell you the main idea. So there are two lemmas. The first lemma, which is simpler, is to say that it says that a spectrum of basically pk minus 1 up down is the same as a spectrum of pk down up. Okay, so sorry, my cue is playing if it's noisy. So basically the way to see it is that we have this bipartite graph, pk down, both pk down up and pk minus 1 up down are oscillating between levels k minus 1 and k. One of them starts from k minus 1, goes to k, and come back to k minus 1. The other one starts from k, goes to k minus 1, then comes back to k. Because you have a bipartite graph, basically these two random walks correspond to random, sorry, because you have a bipartite graph, its adjacency matrix is sort of adjacency matrix of, let's say, xk minus 1 and xk, like this graph you have here, the adjacency matrix look like 0, 0, pk down up, and pk minus 1 up down. So you can just prove for yourself that whenever you have such a matrix, the eigenvalues of pk and pk up down, pk down up, pk minus 1 up down are exactly the same. Okay, so this says that these two are the same. Now, where does the action happen? The action happens between pk of up down and pk of down up, and the second lemma is that is the following: is that, let's say you define mk to be let's write pk up down to be equal to identity over k plus 2 plus k plus 1 over k plus 2 mk. So what do I mean by this? This is the non-lazy up-down k up-down walk. So as I said, the up-down walk goes back to the state that you start with, the probability 1 over k plus 2. This is the non-lazy version of it. mk is the non-lazy version of it. You don't come back. Okay, I take that off. And the second lemma says that the largest eigenvalue of mk minus pk down up is less than or equal to max of lambda 2 of p tau for tau in x of k minus 1. Okay, so this is the most interesting thing. So it says that basically if all of the links of dimension k minus 1 have are a spectral expander, their second eigenvalue is very small. So in our case, we have a 0 one-sided spectral expander. So the second eigenvalue is 0. So in this case, this is 0. So that says that pk of down up is mk is basically less than or equal to, in the PSP sense, of pk of down up. So to put it differently, we get that pk of up down is less than or equal to 1 over k plus 1, or I over k plus 1, plus k plus 1 over k plus 2, pk of down up. And pk of down up, we also proved that it's the same as pk minus 1 of up down. Now we have everything we need to do an inductive proof. We know that we can relate eigenvalues of pk of up down to pk minus 1 of up down. Similarly, you can relate k minus 1 to k minus 2, and so on and so forth. So the main non-trivial part is actually this second lemma, which says that, which sort of relates this eigenvalue of the non-lazy walk to the eigenvalue of the non-lazy up-down walk to the eigenvalue of down-up walk. The proof of this again uses the localization idea and this Garland's method I talked about. You can read it in the notes. It's basically the same idea. And it allows you to say that if every link is a spectral expander, you don't basically pay when you go from, a down-up walk to the up-down walk. So you put it all the way together, you can prove the theorem I talked about above, this theorem. You can prove it inductively, start from 0, go up 1 by 1. Each time you average out the eigenvalue of the previous matrix with 1 over k plus 1. You can easily prove that eigenvalues of pk up down are at most 1 minus 1 over k plus 1. Okay, so yeah, let me stop here and let me know if you have questions.
Thank you, Shayan, for this lecture. Are there any questions?
Can I ask what happens if you're interested in independent sets instead? This will give you something by looking at restrictions or truncations, but if instead you wanted to really just run the up-down walk, but with up and down always being random, can you say something about mixing them?
Sorry, independent set of a matroid, are you saying?
Yeah.
Oh, but you can, sorry. So you can truncate the matroid to a level k and then run it on them, but you don't want to do that? Do you want to choose a uniformly random independent set? Is that
well, uniformly random or with an external field, so they're sort of biased.
No, but is it of the same size, in the random independent set of size k, or
no? I want it to be random in size as well.
Oh, I see.
So this is like sampling the typical example would be sampling a uniform forest instead of a uniform tree for the graphic metric.
Exactly. So one way, okay, good. So one way is to first sample, first count how many, say, independent set of each size are, and then do that. But I agree, you don't want to do that. You want to do it in one shot. Nobody has done this, but I think it should be doable by sort of introducing some dummy elements to sort of homogenize the underlying polynomial. So there is a so if you have one paper, if you look at log concave polynomials tree, there is a polynomial over all independent sets of a graph, which is log concave. But that polynomial is not multi-affine anymore. So you have a variable y raised to the k. But I think that polynomial should be able to, like, we should be able to sort of replicate it in this language of simplicial complexes by using dummy elements. So yeah, that's a good question. Nobody has done it, and I think it should not be so hard to prove that maybe by introducing some dummy elements you can sample independent set in one shot.
Okay, so maybe I should just say slightly more, which is that I agree it's interesting, but I was really wondering about the mixing time, I guess, because in particular, I think you won't you will no longer be able to get very fast mixing times.
I suspect it would be of order of d squared as opposed to d.
That's possible.
There is so I should say, before this paper that we wrote about simplicial complexes, I had an earlier paper to basically generate or to evaluate a real stable polynomial with non-negative coefficient, to evaluate a homogeneous real stable polynomial with non-negative coefficient. So we could do that using different machineries, and we could do it for homogeneous real stable polynomials. Now, for real stable polynomials, there is a simple way to homogenize them. So there is a follow-up to our paper, which basically homogenizes the underlying relative polynomials and then uses our machinery. So that was used to generate random samples of so-called determinantal point processes. And the running time there was n squared, where n is the n is the number of I mean, the determinantal point process can have n samples of size n as well. So I suspect something similar can be done here. There's a little bit of annoyance in homogenizing log concave polynomials. So real state polynomials are easier to homogenize. You can just multiply. If you look at one of the homeworks, I think homework 3, I talked about it. You can basically multiply any monomial by, you can introduce a new variable and multiply any monomial by, co-dimension of that monomial, like d minus the degree of that monomial, the co-degree of that monomial. For log concave polynomial, you also have to rescale. You have to divide by some factorials to make it still log concave. So homogenization is a little bit more annoying, but I think still it should be doable. You should be able to get some d squared probably running time. Okay. At least d squared spectral gap, I think. And maybe even d squared so-called modified log symbol of constants, if you know what that is.
Yeah.
1 over d squared. Yeah.
Thanks.
Are there any more questions? Okay, so if not, then since this was the last lecture of this lecture course and indeed of this year's Prague summer school on discrete mass, let me make some final remarks. Firstly, I would like to thank our sponsors and staff of Charles University and the Czech Academy of Sciences for their help, and in particular to Zdeněk Dvořák, who has been organizing this course with me since the first edition in 2016. It's a collaboration that has worked very well. I hope Zdeněk feels the same way. I would also like to thank our scientific board for suggesting to invite Shayan. We asked the scientific board to suggest a field with recent breakthroughs and a leading expert in that field. And I don't think that there could be a better choice, because geometry of polynomials is something that will be getting more and more attention in the forthcoming years. Big thanks to all of you participants of the school and those of you that attended these lectures and the exercises. I understand that this was a busy week and but I hope that you learned here something new and that it will help you in your research and you will be able to utilize these fields, perhaps in a new field. And last but most importantly, let me thank Shayan for delivering this wonderful course. We understand that this summer was very difficult and we appreciate that Shayan agreed to adapt these lectures to this new virtual format we had to switch to. So let me invite all of you to unmute yourself and thank Shayan with applause for this lecture series. Thank you.
I also would like to thank Jan and all organizers for managing such a beautiful program. Maybe let's all thank them as well.
So thanks again, and I will see some of you later tonight or tomorrow morning in the exercise. Oh, and by the way, so sorry. So I should also thank, that's a big thanks to TAs that helped with Shayan's courses. So this is Cornelius Brandt, Dorna, and Kui. So I think they all, even if they were not your TAs, I think they all deserve our applause as well. Yes, so I will see some of you later tonight or tomorrow, and please, I think with Zdeněk we would like to hear any comments about this new format. So of course we were collecting comments about format in these previous summer schools as well, but this year it's particularly interesting because you know, it's a completely new format. So please, if you have any suggestions or any observations, do write us an email, and we will certainly consider that if it's needed in the future. Okay, goodbye everyone.
Thank you. Bye everybody.
Bye.
By the way, if anybody has questions, feel free to send me an email now or in a month or whenever. I'll be happy to answer.
Okay.
There's a question if there would be any social events.